Hello, so this is part 2 of lecture 5. So in part 1 of lecture 5, we discussed how we might estimate our autoregressive model, our AR1 model, of the dynamics of the 1-year yield by regressing values of the 1-year yield at t plus 1 as our left side variable on lagged values and an error term, and we estimate that first order autoregressive coefficient rho. Once we do that estimation, we have a method of using that model to compute expectations at time t of where the short-term or the 1-year interest rate will be at future dates. And we will use those expectations in constructing our model of the term structure of interest rates, or of the dynamics of the term structure of interest rates. But the other input into the model is the term premia. And we're going to be assuming that the expectations hypothesis of the term structure holds, so that term premia are constant over time. And as we discussed in lecture 3, that means, using the law of iterated expectations, that we can estimate the term premia for different maturities, 2, 3, 4, 5, n, whatever, just as the unconditional average of the maturity of yield n and the yield of maturity n and the yield of maturity 1. And so we just can take all the data we have and estimate these means, and those are our term premia. So we're estimating the term premia from the average slope of the term structure. And then we have these differences of term premia that came up when we discussed forward rates and expected excess holding period returns. So once we estimate these from these unconditional averages, we can construct these coefficients as well. So now we're at a point where we've estimated rho, and we've estimated the term premia Cn, and we've constructed these term premia relevant for forward rates by taking these differences of our estimates of Cn. And once we've done that, we can begin to construct our model's implications for forward rates and longer term yields. So at time t, as we've discussed, under the expectations hypothesis of the term structure, the forward rate at time t of maturity n is supposed to be the constant term premium term, this dtn, where d bar n is supposed to be a constant, and our expectation at time t of where the short rate, or the 1-period rate, will be at period t plus n minus 1. So we can use our econometric model to calculate this term. This term, this conditional expectation, is our estimated coefficient rho raised to the power n minus 1 times the difference between the 1-period interest rate at time t and its unconditional mean. So this we observe at time t, we've estimated this parameter, and of course we can add in back in the mean. So this gives us that value. And we've previously, by assuming that this thing is always equal to its unconditional mean here, we now have an estimate of this term as well. So now we have everything we need to construct a model version of the forward rate. This is what the model says the forward rate should be as a function of an estimated parameter This is the estimated parameter. This is the estimated parameter. And this is the current value of the short rate relative to its mean, an estimated parameter at time t. Or another way to write this same equation is just like this. The difference between the forward rate and its mean is just this value, rho to the n minus 1 times the difference between the short rate and its mean. We can also compute longer maturity yields. You can do that by adding up forward rates, or you could do that directly as we've done here. The formula is a little bit more complicated. You have to use our AR1 model to construct, at time t, you have the AR1 model tells you what this term is, all the other expectations out at different horizons. A general formula is given here from this. So the expectation at any given horizon is just rho to the n minus 1 times this gap plus the unconditional mean. And we've estimated this term premium, again using all the available data for the long run average of the slope of the term structure. And so then we have a model implication of what a longer maturity yield at time t is we have a term premium, we have a long run mean of the short rate, and then this sum or average of deviations, this coefficient times deviations of the short rate today relative to its long run average. And if you solve this sum out, you get this expression. So longer term yields should have this should move up and down with short yields with this coefficient. And then finally, we can consider the model's implications for expected excess holding period returns, which we introduced in lecture 4. And there we said the realized holding period return is the difference between the realized return on buying an n period, a bond of maturity n at time t and selling it at time t plus 1 minus the short rate. And we computed last time that the expectation of this value is just this function of the term premium, which is in fact this constant d bar n. So the key thing is, in terms of what the model says about when is it a good time or a bad time to invest in longer maturity bonds, there really is no good time or bad time because term premium are constant, which means that expected excess holding period returns are also constant. So I'm going to stop here at the end of part 2 of this lecture. And in part 3, we're going to look at some implications of our model for forward rates of long maturities when n is a large number. And what you'll see, what I can preview, is that rho is a number about 0.9. If we start raising it to a high power, then this whole thing should start getting close to 0. And what that will say then is that how volatile the long-term forward rates are around their unconditional mean, it gets smaller and smaller as the maturity of the forward rate goes out, n gets bigger and bigger, because this is one time series that's driving all the forward rates up and down together. And this coefficient is getting smaller and smaller as n goes to infinity. So that's what we're going to discuss, the implications of that in the next part of this lecture.